And in this video I will show you how we can proceed to actually find the solution to the driven damped harmonic motion. This is the inhomogeneous differential equation that I'm going to try to solve, and I have provided a specific function for the force that drives the oscillation. You have to do that. You have to do this in order to be able to solve this differential equation. Okay, in the previous step, I talked about the theory without having defined the function that the force that drives the oscillation. But to proceed further and to actually solve the differential equation, I need to have a function. In this case, I've chosen a simple one, a periodic one, that is the cosine of omega t. Now, to solve this one, I'm gonna do some work. At the beginning, it may appear to be not relevant, but actually it does help in allowing us to solve this differential equation in a somewhat convenient way. So I've rewritten the same essentially differential equation, with the only difference that now I have sine instead of cosine, and instead of x I'm using y, because y will be the solution to this differential equation that includes the sine, not the cosine. Now, using defining z as a function of time to be x, the solution to this differential equation, plus I times y, where y is the solution to this differential equation, what I can do is I can multiply this second one with I, the imaginary unit, multiply that with I, and then add it to the first one. If you do that, then what you get is x dot plus I y, x double dot plus I y double dot, which will simply give me z double dot. And then I have 2 times vita x dot plus parentheses x dot plus I y dot, and this will give me simply 2 vita z dot. And similarly, you get the same thing for the last term. And then I have f naught, I take it out as a common factor, cosine omega t plus I sine omega t. At this point, I want to remind you that if you have a number e to the I theta, where theta is just a number, an angle, then you can write this as cosine theta plus I sine theta. And here, this is what I have, cosine omega t plus I sine omega t, which means I can write this as f naught e to the I omega t. Now, at this point, using zeta as an intermediate does make things a little bit more convenient, because it is easier now to guess a solution for this differential equation. And remember, if you guess a solution and you actually get it right, then you found the solution. So in this case, one reasonable guess would be the constant c to the I omega t. Now, if you take the first time derivative of this, you will get c times I times omega e to the I omega t. And if you take the second derivative of this, you will get minus c omega squared e to the I omega t. Now, if I take all of this and I plug it into here, I will get minus c omega squared e to the I omega t plus 2 vita c I omega e to the I omega t plus omega naught squared c e to the I omega t. And this will be equal to f naught e to the I omega t. Now, if I take out a common factor, I will get minus omega squared plus 2 vita I omega plus omega naught squared. I think C is a common factor. E to the I omega t equals F naught E to the I omega t. And for this to be true, the constant C needs to be equal to F naught divided by minus omega squared plus 2 beta I omega plus omega naught squared. So this is the constant C that I need to include in my solution. Now I do want, I'm going to write the Z again. I do want to remind you that this is a particular solution to the inhomogeneous differential equation. Now here's the thing, okay, I do want to go back and remember what I tried to do. This was the inhomogeneous differential equation that I started with. And remember, I did end up using imaginary numbers during this process. If I want to find the solution to this differential equation, when I find the solution to this differential equation, I have to take the real part. Why do I have to take the real part, and why not keeping the whole thing? Remember, I defined, if we're here, this is what will allow me to solve that. Okay, this is the solution to that differential equation. This is the quantity I'm looking for, and this is the real part of Z. So what I'm interested in finding is this, which is the real part of Z, which is the real part of C e to the I omega t, with C being defined here. Now I have solved and I have found a particular solution to the differential equation. Now I do need to mention there is a lot of algebra that needs to be done, okay, in this process, which I will skip, and I will give you the summary. So at the end, your particular solution to this inhomogeneous differential equation will be A times cosine omega t minus delta, where A is defined by this expression, okay, this is the definition of the parameter A, and then the phase delta as I said, okay, there is a lot of algebra that goes in between what I just wrote and my last step. So there is work that needs to be done. At the end of the day, though, these are the important results. This is the particular solution to the inhomogeneous equation. Okay, but remember, I want to find the general solution to the inhomogeneous equation. And with the theory that I talked about in the previous video, if I take the sum of the solution, the particular solution to the inhomogeneous equation with the general solution to the homogeneous equation, then I have the general solution to the inhomogeneous equation, which is what I'm looking for. And for me, this will be the A cosine omega t minus delta plus C1 e to the R1t plus C2 e to the R2t.